Hello, in today's lecture, we are going to discuss time-independent Schrödinger equation, qualitative discussion over time-independent Schrödinger equation. But before I start, let us take an important discussion. The question is, or you can say the discussion is on the addition of a constant factor or a constant with the potential. We see that the change of the reference does not change overall the dynamical problem. Okay, so basically the problems remain the same. The structure of the problem remains the same. Let's say I want to apply principle of conservation of energy. Factor does not change the overall formulation of the problem. However, in quantum mechanics, things may change. Okay, so suppose one adds a constant V naught energy, or simply potential, then the wave function psi will change by a time dependent will change, and a time dependent phase factor would be introduced in the wave function to make it compatible with newer Schrödinger equation. Just let me help you with this. So basically, what I want to say is that, let's say if my potential Vx is changed to Vx plus V naught, be changed by a time-dependent exponential factor. So basically, if it was psi nu, some time-dependent factor. Okay, so this is my claim. So let us start. So for convenience, let us suppose that which satisfies the Schrödinger equation without x naught, without v naught square. So basically, if this is the del psi upon del t is equals to minus hk square upon twice m del square psi upon del x square plus the potential is changed to Vx plus V naught. So the new equation should be some iota hk. Let's say this wave function, I'm claiming that this would be changed. So I'll just write it as something like psi naught minus hk square plus V as a function of x plus V naught times psi. Okay. Now my claim is that should be of this form. That is, for a time-dependent Schrödinger equation, if a V naught is added to a potential, then the Schrödinger equation, that is the time-dependent Schrödinger equation, would change. And instead, as compared to the old, you did not have a V naught, the new wave function will be the old wave function times a time-dependent factor. So this is a time-dependent factor, which is right or wrong. Okay, so let us see whether my claim is right or wrong. So basically, so let me write it as equation number 1. And let me see replaced by psi naught. And what is psi naught? Psi naught is psi exponential of minus iota. Let us. Okay, so if this satisfies the Schrödinger equation, then iota hk equals to iota hk del psi upon del t exponential minus iota v naught t upon hk, and again minus iota v naught upon hk, and then you have this psi, and then again I have it. Okay, so basically iota hk del psi naught upon del t is equivalent to writing iota hk del psi upon minus of iota v naught t upon hk, and then plus this hk can v naught psi exponential of minus iota v naught. Just think about this. Iota hk del psi upon del t from equation number 1. I can use this. So using 1, I can write what? I can write this particular bracket. So this is like iota hk square upon twice m del square psi upon del x square plus vx psi times hk plus v naught psi exponential of minus iota v naught t upon h. This is equals to psi naught. is quite equal to psi naught. Now this is equal to psi naught if psi naught. And see, this is partial derivative with respect to x. So I can take this inside. With respect to time, we are differentiating with respect to x. So basically, this even if it goes inside here, it's not going to. For example, if I'm writing del square psi upon del x square times exponential square upon del x square of psi exponential minus iota v naught t upon h cat. This is psi naught upon del t is equals to minus h cat square upon twice m. And instead of this, I have absorbed this inside psi naught upon del x square plus again vx psi naught. And again here, what is this? This is again psi naught. So naught satisfies this Schrödinger equation, which is nothing but okay. So psi naught satisfies a differential equation where your potential v naught. Okay. So no longer your psi will satisfy. So basically, what who will satisfy potential is increased by an amount v naught. Now the change of Schrödinger equation is given by psi is equals to psi naught is equal to psi times exponential of, you should remember. Okay. So if a constant potential v naught is added to a time dependent factor, so your wave function gets altered. Okay. So if you change the potential, if you change in quantum mechanics, the wave function would overall problem description remains the same. However, here it changes. This is one thing that you should remember. Take the expectation value. If you're trying to take the expectation value of a dynamical variable, however, would remain the same. Why it remains the same? See, because you understand that basically what happens is if I want to take an expectation value of, let's say, a cap, so it is equals to minus, this is like psi star, and there will be a cap, and there will be, this is how it will be. Understand psi naught is psi naught. So this will be like psi star, and now you will have exponential of iota v naught t upon h cat. Exponential of minus iota v naught t upon h cat. Now, if I, after all, and mostly are going to be either functions of x or p, either going to be the functions of x and p. So with respect to x, it is not going to operate on this. It is not going to operate on this. So basically, star, the psi naught star will become psi star. A cap will remain a cap. Psi naught dependent factors which are dependent on time, which are not dependent on x. So I can simply multiply them here. So this is iota v naught t upon h cap. So basically, what will happen? So this will get cancelled, and you will get this with your older wave functions. So like both of them are same. So a constant potential is added. Let's say v naught. No doubt, the wave function would change. The older wave function times the exponentially some time dependent factor. But understand by evaluation of a dynamical variable, uh, because of this conjugate thing, this particular thing upon h cat times psi star, and psi naught is simply psi exponential minus iota v naught. Overall, the expectation value remains invariant to this change. Okay, this is another important point that one should remember. Concentrating more on finding the wave functions provided potential is given potentials. Okay. Now let me just give you an example where you can also find, let's say, ground state energy. So assume that ground state eigenfunction Ix is equals to a times secant hyperbolic lambda x, where a and lambda are constants. Then we want to calculate the ground state energy. So in previous lecture, we actually found some potential, calculated the wave function itself. Now here I'm interested in finding the ground state energy 0 as x tends to infinity. Okay, so how to go about it? So okay, so now a little bit of right. I will have to operate h cat over it, right? And clearly the wave function clearly depends upon clearly formulas, so that if they are useful, then you may use them while doing this particular problem. Is to remain aware about it. So if I would be doing derivative of sec hyperbolic x into tangent hyperbolic x, and the derivative of tangent hyperbolic x is simply secant hyperbolic square x. Property that you can think of is that 1 minus tan hyperbolic square is simply equals to sec hyperbolic x. Okay, this is clear. Now let us start with the We want to calculate the ground state energy, okay, from the given hits. So now, as you're aware, so I'll start from here. So I'll start on by claiming energy. This E would be the ground state energy. What is Hket? Hket would be minus Hket square. Hket means this Hamiltonian operator I'm saying, del square upon lambda x. So what I'll do, I'll first take the derivative. So I'll first do this and the energy operator when acted upon on this particular thing. So basically it is like minus Hket square upon twice m is del by del x a. And what is the derivative of secant this thing? So I minus okay, this is one thing. Now, if I again differentiate it with respect Hket square lambda a upon twice m, and then again I'm going to differentiate it. So minus lambda secant hyperbolic lambda x into tangent hyperbolic lambda x. Already it is there, so this will be like, and then again plus of, because see, this negative I have already absorbed. This hyperbolic x tangent x, and 10 hyperbolic x derivative is again secant hyperbolic x. So this will become secant hyperbolic. It would indeed come with lambda because of the chain rule. So overall, I can write that this would be equal to Hket square lambda square a upon my 10 hyperbolic square, because I just want to change all these things in secant hyperbolic x, because so it would be minus secant hyperbolic lambda x. And what would be 10 hyperbolic square? 10 hyperbolic square lambda x, it would be 1 minus of secant hyperbolic cube lambda x. So it is equivalent to writing this Hket square lambda square upon twice m. So this is 2 times secant hyperbolic cube because this is my hyperbolic. Okay, so this is simply kinetic energy operator acting upon the, if I want to write the complete thing, this will be like Hket square lambda square upon twice m. If I take 2 times secant hyperbolic square lambda x minus 1, and okay, so I have plus bx times psi is equal to E slash them off. Now, there was a hint given to you, and the hint was that as x tends to infinity, your potential goes to 0. If x tends to infinity, potential goes to 0, then, and also that as x tends to infinity, clearly, okay, until unless specified, I will take lambda to be a positive constant. Okay, this will be equal to 1 upon cos hyperbolic square lambda x, and which will be equals to 4 upon exponential minus lambda, plus a whole square. Now, as x tends to infinity, lambda is negative, lambda is positive. And as x tends to infinity, this is positive, so overall would go to 0. So what remains is the total energy of the system, that is right now in this Hket square lambda square times 2m with a negative sign. I hope it is clear. Okay, state energies. So we've done a few questions on or problems on, or you can say illustrations on finding the potential supply of wave function. From there you can find the potentials also. But here ground state eigenfunction, ground state energy provided ground state eigenfunction is given to you, because this is an eigenvalue problem, right? Hket psi is equal to E psi. So solution for this eigenvalue problem. Now let us move a little bit further and try to make some discussion on the equation. So as you're aware that we've already done this part, but now let us discuss some qualitative aspects. Okay, so qualitative discussion on time-independent Schrödinger equation. So as you're aware that for the large class of dependent upon x, okay, so in our discussion we are not going to discuss right now potentials which are completely time dependent. And we've seen that while we were solving this equation, that is to Hket psi, using method of separation of variables, we found that it reduces to a problem where you do the equation and a time-dependent equation, which time-dependent expression, which is like et upon Hket. So basically, the total solution in that particular scenario is written as simply psi as a function of x times pi t, which is where e this eigenfunction. This E is the corresponding eigenvalue corresponding to this eigen, or you can write your solution. Now let us discuss some very qualitative part right now. This solution is referred to as stationary solution, or we say this represents a stationary state. Okay, so what is a stationary state? I'm going to just write it down. So a stationary state of energy E may not be stationary, but right now I'm just writing it, and then we'll see that case also. That is a state psi of x comma t that takes the form of this iota et upon h kit, where psi x can be any like psi x is a wave function with of complex numbers. That is, it is in general a complex valued function. I hope it is clear. Okay. Now, why this is called as a stationary state? What is a stationary state? A stationary state is a state with energy E belonging to dependence is carried by this exponential prefactor. In a stationary state, exponential prefactor, or you can, so exponential prefactor, as you can see, carries the time dependence. Okay, it carries the time. This stationary state because all the physical observables, okay, because the physical observables of the state, of the state happen to be time independent. And for instance, let us just think about the norm of the state. Let us think about the norm mod whole square. And what is psi mod whole square? It is psi star psi. And clearly, it will be equal to times psi. So basically, this is like, and this is psi star. And then I'll have again psi. And this. So basically, this cancels off, and you're left with this. So one can see that this norm of the state, time dependent, drops out. Now, if you remember, I very carefully told you that the state where psi of x comma t takes the form of psi x into exponential minor called as the stationary state because the physical observables of the state happen to be time independent. With this E being a real entity. Okay, why am I so stuck with E being the real entity? Okay, so it is the norm of the state. Even if I want to calculate any expectation value, let's say A of that, I know that this time dependence will not come inside because I will have to do this psi star A cap psi. And while I do this, I know that in evaluating this, and so therefore the name comes as stationary state. Okay, so in general, remember that the total wave function always carries to find the expectation values of the operators corresponding. Find that this time dependence drops out, and therefore these solutions are called as the stationary solutions or simply stationary states. Okay, so why do you think that energy should be real? Why do you think that energy should be real? So let's prove this thing by contradiction. So had the energy E been a complex number, so had the energy being a complex number, still remains stationary? Let us see. So to this end, I'll assume that let us say that my E becomes E naught, and gamma obviously belongs to real entity, but overall energy now belongs to a complex number. And as simple as norm of the state. So now my stationary, if it all do that the dynamical variable, that the expectation value of any dynamical variable or not, let us see if E becomes a complex number, does the time dependence drop out? So what would psi of x times E exponential minus iota E naught minus iota gamma. This is what. If I just try to find the norm of the state, if I just try to find the norm of the state, what it is going to be? It is going to be psi star exponential iota E naught minus, so upon hk also would come upon hk log minus iota E naught. Okay, so if I do a psi star, okay, my mistake, let me keep it in general at first. So that will be a better thing to do. So let me keep things in general. Hopefully E, so that things will remain in general, and then we'll solve it only. Okay, so this will be like exponential of minus iota in here. So it will be like iota E, and I'll take a conjugate here. So E star minus ET upon hk. So basically, what will happen? The norm of the new state is psi mod whole square. This is absolutely fine. Now here I will have exponential of iota E star. And what would be E star? If E is this, then E star would be, or E conjugate would be simply E naught plus iota gamma. So E whole square exponential of iota, and this will be simply 2 iota gamma. Norm of the wave function, where the wave function is accompanied by a with energy E being complex number. This norm can be written as psi mod whole square exponential of minus 2 iota gamma. Time dependence does not run out, and it no longer remains a stationary state. And it no longer remains a state. The state is stationary, accompanies with itself that E should number, because E cannot belong to the set of complex numbers. Okay, I hope it is quite clear to you. Okay, so in general, psi as a function of both x and t is equals to psi x t upon h. This is how you write the solution mostly. Okay, now this psi x happens to be a solution of time independent Schrödinger equation. Clear? Okay. Alternative way of looking at this is see. Okay, alternative way of looking at this is that for all writing for all normalizable solutions, and by here I mean this this thing, the stationary solutions. This energy E must be a real constant. Must be a real constant. Okay, it must. If it is normalizable, then norm must be like norm of the wave function should be equal to what? 1. Or simply, if I state dx minus infinity to plus infinity, I must get this equal. Now E is no longer a real constant. Let us say that E is my, again this similar one, E naught minus iota, not as psi star psi mod whole square dx from minus infinity to, because now I'm integrating with respect to x, so the time dependent factor I'm taking outside, minus of 2 times gamma t upon h cat, and all of this is equal to 1. So this is a definite here as a constant, but this will induce a time dependent term here. So if for the consistency on both sides, it is gamma is equal to 0, it implies that E would be again D. So take any sort of argument, one should understand particular for not all normalizable solutions, or for all normalizable stationary solutions. Take while we do the method of separation of variables, this E must be a real constant. This E must be a real constant. Okay, this is quite important. The second point regarding this particular you can say discussion would be these states, all the stationary states are the states of definite total energy. Okay, now let us see how. So I already stated that stationary states are the solution for this. H get psi is simply equals to of definite energy. What am I expected to find? I am expected to find the expectation value of this from simply psi star h get psi dx, which is simply equals to what? It is simply psi would simply give you E. So I'll take E outside dx, and this is simply equals to E. Okay, so it's a real constant. Okay, moreover, if I just operate h over this, so h square, we get this equivalent to E square psi. Okay, and if I say that, what would be the expectation value of h square? Next, if I want to check the variance in H, variance in this measurement of H, I can simply write it as C square minus E square. Okay, so therefore I can say that if sigma is 0, then the spread from the mean position is 0. This implies what? This implies that there is no as such spread in the energy measurement of the total energy. Every measurement of the total energy will return the value E. It implies what? It simply implies that a separable solution which when acted upon by Hk will always return the same value. Or simply I can say will return the energy E here for that matter. Means what? It is the distance from the mean. Okay, so this is the distance from the it quantifies the spread of the distribution. So if the distribution does not have any spread or that there is no as such, you can say uncertainty in this measurement, or you can return a definite energy E. So there is no as such uncertainty. So it will always return your definite energy E. The third point is can be written as the linear combination of these stationary states or stationary solutions. Yields me infinite collection of solution, let's say psi 1, psi 2, psi 3, dash, 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 E2, E3, so on and so forth. Then the wave function psi x exponential of minus of iota E1 t upon h squared. Similarly, if I want to write psi 2x exponential of minus iota E2 t upon h squared, and so on. Okay, and we have seen that Schrödinger equation is a linear equation, so therefore the more general solution would be of this form. Okay, now to summarize, I can say that I'll be given a potential Vx. Using this potential by applying time independent Schrödinger equation, I can obtain a x at t equal to 0. Having known this, I can always find a wave for all subsequent future times. So the strategy is quite clear that one would solve a time. If let's say it yields you different solutions, let's say psi 1, psi 2, psi 3, E3, E4, so on and so forth, then the solution psi x comma t for all future times can be simply written as psi minus iota E and t upon h squared, and then you can take a sum of all of these. Explain you this concept. If there is any doubt, please let me know. Okay, so I have till now stated almost 3 properties. So I'm just with regards to the solution. So I'm discussing right now qualitative discussion on time independent get del psi upon del t h get psi. With the method of separation of variables, I obtain a states times exponential of minus iota et upon h. Right now, this particular state exponential minus iota et upon h, and this is called as the stationary state. Here psi x belongs to set of is encompassed in this particular exponential term. Why this is called as the stationary state is carried out by this exponential prefactor, and when we are trying to find the expected state, we find that this time dependent factor goes away, since this time has the stationary states. Also, we discussed that this energy E must be, if it is a complex number, then it will no longer remain a time it will no, you can see that the time dependence will not drop out. Okay, this is one thing. Also understand that these states get on them, I'm going to obtain a definite energy E. In order to establish this, I went on to investigate the variance in energy measurement and energy you can say in terms of Hamiltonian operator. So basically sigma, that is what the spread from the mean position. So basically h square, expectation value of square minus 0. So there is no as such spread of the distribution or no as such uncertainty in the measurement. So basically return a definite energy E. This is another property. Now, the general solution can always be, and this comes because you should understand that the Schrödinger equation is a so therefore linear. So if the solution is Ix, then linear combination will always be a solution owing to the linearity of the Schrödinger equation. Now, if I know that it's a state with energy E2, psi3 is a state with energy E3, then psi1 x comma t can be written as psi1 x energy eigenvalue corresponding to this eigenfunction. Okay, so understand in summary, we will be given a potential Vx and let's say a starting wave function psi x all future times, for which I would require to solve time-independent Schrödinger equation. Let's say psi. I will be able to write my wave function for all future times, but